Okay, I've been trying to do a YouTube live for the past few days, which weren't successful, so I thought I should record a session. So I will be giving you a summary of a problem that I discussed in one of my sessions, MYP assessment sessions. So if you are interested in how processing and evaluating is assessed in the MYP assessments, so this session could help you out in that. So I'm uh, I'm going to start right now with the experiment. Um, so this is an experiment that I designed for collecting data on the displacement and time intervals of a drone. So we will be collecting that data and then processing it and then evaluating it and looking at the model and the problems with the model. So that would give us insights into collecting data, tabulating it, creating models or graphs from it, and eventually coming up with an equation that could explain the motion. So let's get to it. This is the experiment. We will start the experiment and I'll start, so at 0 seconds we have the position is at 0 meters as you can see. Um, the drone is at 0 meters and now I'm going to start it. And it will start moving. I'm not sure what is the behavior of the motion, but we will find out. So start. And I'll start collecting data by clicking on this button. So every second, the exact displacement of the object is being noted down. So I'm going to collect a lot of data and I'm going to pause it. Okay. So you can see that I have collected some data on the motion of the object. And a problem like this is, I saw a problem like this on an e-assessment. So I'm going to show you what assessment was that. So here is that assessment. Okay, so the data is given for time and position, and then it has also been graphed for us. And as you can see, the time and displacement data is available. And the problem with the model is that if you plug 0 seconds into this model, zero will be plugged in the place of t squared, and it will be plugged in the place of t as well. That would mean that the position of the object at 0 second is 16.2, which is not correct physically, because it clearly tells us that the ball was released from 0 mark. So is the model lying? What's the problem? How does these problems appear in model? That's something that we will be discussing in today's session. What I mean by the problem with model, I would like to discuss it mathematically as well. So, okay, let's go back to the experiment. The data is available here. So I'm going to copy this data and we're going to process this data in a spreadsheet. Although the table has already been made for us, you can see that the quantity's name and the unit has been mentioned in the bracket. The displacement quantity and the unit meters has been mentioned, and that it has been given a title. So these are three things that we should be careful about when designing tables in an IB MYP assessment. Okay, so if I take this data to sheets and I paste it here like this, that at 0.7 second, I mean, there's one data point missing, so I should add it. At 0 second, we know that the object was at 0 meter mark, right? Okay. Now we will take this data range. I'll talk about the rest of these columns later. And we will insert a chart and bring it here. And we will tell it that on the x-axis we have time, and on the y-axis we have the displacement. Okay, so the horizontal axis is titled as time in seconds, and the vertical one is displacement in meters. So important stuff for a graph. And now let's take a look at fitting a curve that would explain this motion. So we need a mathematical function that would tell us, that would establish a relation between time and displacement, that at this time the body was at this position. We have experimental data on that. We know that at 0 second the object was at 0 meters. At, let's say, 2.5 seconds it was at 12.5 meter mark. But what happens when you don't have enough data? What happens here? What if someone asks us that where was the object after 15 seconds? How do we predict that? To predict that, we need to have a model that we can plug in time into, and it will give us an output of displacement. So how is that done is the question. It's part of the evaluation of data and interpreting data. To do that, we need to go to series and we need to add a trend line. Now you can see that this is also one way to describe the graph. That the graph is, the distance is increasing, but it doesn't capture the whole truth. because if I use this model, it's a linear model, and you can see that it is not telling us the truth at many points. It is only telling us the truth at this point here and at this point. So that's no good. I mean, even there's a saying about a faulty clock that even that tells correct time twice a day. So it's that kind of a graph. So that's of no use to us. So what do we do then? Instead of linear, we could try exponential. You can see that the model has changed from linear to exponential now. Do you think this is better than linear? Yes, I definitely think it's better than the linear because it is overlapping with the original data line for the most part. The dark line is the actual data that we have, and the light line is the data that is the projection, is the trend line, is the model. Okay. Question is, how does the model perform in the place where there is no data available? So beyond, let's say, 10 seconds or 11 seconds, what's the situation there? So let's take a look at that. We will use this model to predict, let's say, for 14 seconds. And then we will go back to the actual experiment and do some tests to see whether this model is helpful or not. But before doing that, I would like to show you a few more trend lines. We'll try a polynomial one to see if there is something that fits even better than this. Okay. So after exponential, I think I need to move myself and show you that I was changing it from here. Okay. It was linear and then exponential and then polynomial. I think polynomial isn't performing very well in the starting 5 seconds, but beyond that, it is performing very well. And the reason I say that is I have hoped that beyond this point where data isn't available, it will be performing better than the exponential one, because the exponential one was rising faster, way faster than, the actual data. In my prediction, the actual data won't be speeding up with that pace, because you can see that's going to grow up way faster than the actual data. That's my educated guess. But you'll see why I'm saying this. I'm saying this from experience, because exponential graphs, they are compounding in nature, and yeah. Logarithmic? No way. Power series? Well, moving averages? Well, we can talk about these later, but I don't think these are relevant for you. We can just make a judgment, because the only tie that we see is between exponential and polynomial. So what I'm going to do is I'm going to pick up both the models. So this is the model for quadratic, and the other one is for exponential. Okay. So we have a quadratic model. Let me note it down. For motion of an object, and an exponential one. I'm going to be doing the calculations with AI so that we can save some time. So I'm pasting the quadratic model, and I'm also going to take in the other model, which is exponential. Okay, I'm going to take this one as well. I'll ask it to use t instead of x, because we are dealing with time. Use t instead of x, and the output should be s. S for displacement, s of t, right? And we will use both models to predict for, let's go back to the experiment and actually do the experiment before that, or because I won't be able to log in data for an exact second. So if you can see this, I will resume the experiment and collect some more data. So we have data till 10.8 seconds right now. And if I resume it and I take some more data, okay, now I'll just see that I have a data point for 14 seconds. I won't see what the value is, but for 14th second. Okay, let's see the outputs, and we will compare it with physical reality. And you can see that our first model was this. That is a quadratic model. The second one was exponential model. You can see e to the power of something. Now, we will make a prediction for 14th second. Or 14 seconds. So the quadratic model, it gives us the value of displacement to be, it plugs the 14 into wherever t was, and it gets an answer for s of 14. So the output for s of 14 is, wait for it, 298.49 meters. Okay, so hold that value. Let's do the exponential one as well, and it gives us 495.99 meters. And now let's go back to reality. What actually happened in the experiment is of interest. 14 is 320 meters. So let's see which one is closer. So the quadratic one is 298, almost 300, and the reality is 320.2. Whereas exponential is way off. It's 495.99 meters. That would mean that exponential model is not useful for situations in which a car is maybe accelerating Well, we can have situations in which, exponential functions can apply in a piecewise situation. I mean, I'm sure you have heard the word piecewise in your math lessons, that when a function is valid only in a specific domain, let's say between 5 seconds and 10 seconds, and maybe we can find out where the function is most relevant, most suitable. Let's take a look at the sheets. So now let's talk about the other few columns that I have made in this. What are these columns? As you can see, this is the time, this is the displacement of the actual experiment, and this is the model's prediction. Now, the model predicts 16.2 here, because this is the model here, the quadratic model. I think I've done this experiment before and I'm using the old model right now. So I'm going to update the model, and then I'm going to write the model, the one that we were looking at, the quadratic one, into this. There you go. So this is the model. If you can compare it with, by going back into the video, that here is the model that we have. So you can see that our model is predicting, and I'm going to paste this entire thing all the way down. Okay, so this 9.95. Why is the model doing that? We know that at 0 second it was at rest, so 0 meters. But the model is saying 9.95. Do you see this 9.95 here in the model? This is the y-intercept. And it seems like there is an extra bit of height in the model. And that you can see from the graph here, that even though the real data at 0 seconds shows a 0 meters, this 9.95 meters height is being shown by the model. And that's what you can see in the mathematical function as well. Now, error means the difference between the actual value and the measured value. So the model is measuring or giving an output of 9.95. So the only problem is in the first data point, because it's getting divided by 0 in the end. You can see that the absolute error is 9.95, but when you find the error percentage, you have to divide by the original value. So the absolute error is found by error, how much error you have, and what's the original value, which is 0. That's why you're getting an undefined thing. Okay, so you can see that based on the maximum error, I should have chosen red, by the way, but you can see that the maximum error is 185.77, and as you go to smaller errors, you get the color to be different. So you can see that this model is performing well in some scenarios and not so well in the other scenarios. So let's take a look at where the error is less than, let's say, 5%. Maybe that's an acceptable range. So we can see that as we move beyond around 10 seconds, the error is very small. This doesn't make sense, by the way. Maybe we haven't pasted this correctly all the way down. Okay, now I can see that there is a region, this data region you can see all the way from here to, I can go all the way down. That's good. This region is a domain which lies from the 4.9 second all the way down to 10.7. So roughly between 5 second and 11 second is a region where the graph agrees to the data more or less. So you could make a piecewise function saying that this model is explaining the behavior of the moving object better in this region compared to the rest of the domain. Now you can visually see it, that the trend line, the light blue line, is betraying the data between, let's say, 1 and 5 seconds, but between 5 and 10 seconds, and even a little beyond that, it is agreeing with it. So this was a brief exercise in collecting data, evaluating it, and if you get problems relating to collection of data, what things you should keep in mind. And if you want to practice in a real exam simulated environment, you can reach out to me and we can have such assessments. And if you have a cohort of students who want to have some practice for e-assessments and subjects like maths, physics, and could be MYP subjects or DP subject, you can always reach out to me and we can have these sessions. All right. Thank you.